So the idea for today is to talk about more about morphisms. We will see an example in which you define morphisms in affine pieces and then glue them together to create a morphism. Actually, that's the tool we will do the whole time. I will just take that way to construct morphisms and just do all with that. So yeah, that's I think it's a cheating way because you are not like really using the definition and describing what's going on at the level of shifts, but just using the fact that you can work in the affine pieces. And in the affine pieces, if your target is also affine, then you have a correspondence on rings, homomorphisms of rings, and that's what I will do. So at the end, this talk is just homomorphisms of rings. All right. So from last time, and maybe a couple times ago, we've been defining what is a morphism OX between two schemes, and we have the ingredients that pi is continuous. I apologize if I say p, I mean pi. My mind doesn't work. In Spanish, this is called p, so I just think in Spanish, sorry. So continuous map of topological spaces. We have some pi sharp from O, Y, I think OY to pi OX. And then we require that this should be local. OQ, the level of stacks, where pi of P is Q. This is local. Okay, I just want to spend some time to write this and say, okay, we will not use that. We will just, the cool facts of this is that morphisms glue. And the important fact we're using is also that you have these equivalence between categories of morphisms of affine schemes. Schemes. They are in bijection with morphisms of rings. All right. Yeah, so far I will just gonna jump into these two things, and that will be how we will define morphisms. So let's start with an example. So let's construct a morphism from a n plus 1 minus 0 to p n k. We'll try to describe one morphism that we could do by taking the affine pieces. So define dxi, which is a spec of k x0, xn, localized at xi. And then I will use this definition to say spec k x0, xn, xi, and take the 0 piece of that. 0 pieces of that. By these maps, but these sets or schemes, I'm thinking inside of an and an plus 1 minus 0, and here I'm thinking on p and k. Good. So we have the natural morphism from k x0, xn, xi0, the inclusion into k x0, xn, xi. So we know that this describes a morphism in the other direction in schemes, and those are which I will call pi I. So they come from dxi to dxi naught. right? So we have that. We have the commutative diagram. I'll just write the order I have here. X0, Xn, Xi. And this inclusion here, okay. Oops, I have it in the other direction. Xn, Xi 0. We have these guys in the middle that are those ones that are helping us to construct the gluability part. Okay, X0, Xn, Xi, Xj 0. And then, oh my God, Xn, Xj, and K, X0, Xn, Xj 0. All right, so all of them are inclusions, and we also have maps this way, which are the localization maps. I'm not giving names. Well, sometimes I will give, but those maps are what you think they are. So this one's inclusion. These ones are take a polynomial p over xi. Say this has degree L, and then you send it to p xj L, xi xj L. So, okay. Yeah, these are localizations. These are inclusions. One thing that confused me is that inclusion is, when you think on schemes, is not the usual inclusion, but localization is, right? So these localizations are giving us the inclusion on the version of schemes. But, okay, before going that, this is a commutative diagram. If you include and then you localize, is the same as if you first localize all these localizations and then you include them, you get this part of commutative diagrams. So we can translate this into schemes.
Yeah, sorry for a trivial question. Can you
Yep.
tell me what are 0 parts?
0 parts are just, these are fractions,
Yes.
but just they have the same degree.
Ah,
They are, yeah, numerator and denominator with same degree.
okay.
Okay, good. Okay, so we have dxi, and here dxi naught. Then in here dxi xj naught, dxj, dxj 0.
Sorry, but when
Yep.
you're saying fractions, you mean fractions of the form p over xi to the L. So
Yeah.
now you're just demanding the p's of degree L.
Yeah, in here I'm thinking, yeah, this guy is a polynomial of degree d, degree L. And then in here,
No, one moment. No. It's on the right. On the right-hand side is of degree L.
oh yeah, sorry. Yeah, in this context, yeah.
Yes. Okay. Okay. Thank you.
All right. Okay, so I'm just reversing all the arrows. Okay, so that part is giving us these commutative diagrams of morphisms and schemes. And now the cool part is we can complete our map, our diagram, including all this opens into P and K. And the good part is we don't need to worry because these localizations are actually translated here into inclusions here. So, and these are also inclusions, so including twice, including a set into another and then into Pn. It's the same as just include. So these parts of the diagram are also commutative parts. Why did I do all that? Well, because we want to glue the things.
And so these natural maps from dxi(xj) to dxi(xj0 is just what, homogenizations of some kind?
You mean this one?
Yeah, for example.
This one comes from this map, which is take the preimage of a prime ideal. Remember that this relation that we have between morphisms in the affine case is, take the preimage of prime ideals. Good. Okay, so yeah. So we want to make sense of, let's take pi I and restrict it to dxi dxj, which is dxi xj. So that's why we want them to work with this particular open sets. But then this map is actually, you start, our pi i's started with in this part of the diagram. You can think on pi i's if you want, put them at the inclusion and put them inside of pkn. So all this map in here is our pi I. I'll just do it with purple. Well, without this one. But then when you restrict to this open, is all this is that that morphism I write in there. So it actually is the same, thanks to this commutative diagram, is the same as going all this way down, which is pi j. Okay, and this is the part when you just wash your hands and say, okay, they glue to morphism pi from the whole thing. When you glue all of them, remember that they make a cover for a n plus 1 minus 0 to p and k. Okay. Moreover, you can say how's this morphism, and this one sends the tuple xn plus n to the element here, x0, xn. Okay, I don't know if this is obvious that this map would be this one. For me, I had to think on that I restrict this map and actually I get the pi i's maps and see that, yeah, they agree. So if they glue, they should glue to the same morphism as this, so this is correct. But I don't know if there's a simple way to see, oh yeah, this is the map that is what it's doing at the level of points. So this strategy, as I told you, is kind of like avoid the old definition and come up with a covering by affine pieces and just describe morphisms at that level and glue them. So yeah, and once you glue them, it's just there exists that morphism that Nick described, the method to glue morphisms. All right.
Question?
Yep.
Why isn't, so you have on this first commutative diagram here, why isn't the maps on the left, why aren't those also inclusions? Why are they different? Shouldn't it just be like a restriction map, which is just typically an inclusion?
Yeah, I think you can see it in the both ways. You can think them, these are like fractions where the usual relation, the numerator times the denominator equals. What I mean is you can think of this inside. This element would be the same as this one if you work with the relation on localizing here.
So what's the exponent in the denominator there? Is that also an L?
Yeah.
Okay. Oh, so you can just cancel the top and bottom.
Yeah, exactly.
It's just a matter of whether you insist on always writing your denominator to be powers of xi, xj, or not.
Okay. So
Yeah, so at the end it's kind of...
I thought it was a different exponent.
No, sorry. Yeah, it's all my bad with my writing. Sorry. Okay.
Yeah, it is basically just an
Yeah. Mm-hmm. It is, but you also can see it like localizing, like, yeah. Anyways. Okay. Right. Okay, so that's our first example. I think a lot of part of my talk is just examples. The second part that we saw last time was the notion of as schemes. And we saw that this is a category in which the elements are schemes that comes with a morphism from X is a scheme, and it comes with a morphism to S, morphism of schemes, and we will call this morphism the structure morphism. a structure morphism. And we also say that if we have two S schemes and we want to construct a morphism between them, we require that the morphism we are creating should make this diagram commutative. So it should respect the structure as S schemes. Okay. So let's construct some structure morphisms. So let S be a finitely generated grade A algebra, where A is a ring. We can construct a structure morphism. As follows. So I haven't said where. Well, I'm thinking structure morphism approach to spec A. Okay. So again, what we will do is just cover this scheme, approach S, by affine opens. So remember that we can cover, let's say, the generators as an A algebra of S are x0, xn. So we can cover this with our dxi naught. I'll just put 0 to n, whatever generators you pick. And the way we will construct this structure morphism is, again, looking at morphisms in these schemes and then see that they can glue. All right, so to do that, since S is finite, it's an algebra, is a algebra, we have a map. Let me just write what are these dxi's. So dxi0 is the same notion as before, but we're thinking on the ring is at 0, is S, we are localizing at xi, and then we are taking the 0 parts of that localization. Okay, so you can maybe guess what we will start, how we will relate, how we come up with a morphism, and it's thinking on the ring case. So since S is an A algebra, there is a morphism from A, morphism of rings from A to S. And we can extend it to map A to the localization. I don't know if I did give a name for that. Probably pi I. Okay, so from these maps, then thinking on the schemes, this induces the map dxi naught to spec A, which is, I'll call it pi I. And the idea is pretty similar on seeing how these maps actually glue. So all right. I'll just call this map the same as this one, but just different meanings. One is in rings, the other is in schemes. So we have this map to Si xi0, and then our pi j xj0, and then localizing again, and xi xj take the 0 part. And this diagram, again, is commutative, so we can translate it to say in schemes that we have spec A, dxi 0, dxj 0, and dxij 0. So this one also is commutative. And this part of the diagram here, for example, is pi I restricted to the open dxi xj. And if you go the other way, then that is the restriction dxi xj. So they agree in overlaps. So you can glue them and get a morphism. So we can glue and get a morphism from approach S to spec A. Okay. Yeah, I think there's no like a way, or I don't see a way to describe like how it looks like at the level of points. So what point is sent to what, unless that you take the point and see which open it is and describe the map in that restriction. Yeah. So, but that's a map. All right. Good. So let's see another example. And X be scheme and P a point in X. There is a canonical morphism from the stack OXP to X. Okay, so this morphism, first we think in the case where X is affine. So in this case, P is a point that is described by a prime ideal, and this OXP is our AP, localizing at P. So we can we can come up with the map from A to the localization that takes any element to A over 1. And this produces a morphism in the schemes. So we will have a map from spec OXP to spec A, and then we just include it into X. So this composition is when we refer to the canonical morphism, we refer in the affine case to this construction. All right, good. In general, for any X, for any scheme, so we can think on P inside of some affine open. As I told you, all this is just put it down into affine opens, or affine opens. So this gives you the map from spec OXP to spec A, and then we include it into X. But this could have like the problem that it depends, that the map depends on the open that you are working with. So I think I didn't give a name for this, but I will call this the epsilon map. So we want to show that if P is in another affine open, the map that you get from this construction is the same as the map you get from I mean, that it doesn't matter what open you take. So you will have, with the construction, again, a map spec OXP, but now to B, and then to X, using the enclosure. Okay, so any idea of how we check? How we can like verify that these two maps are the same? Yeah, look at the intersection. And the good thing of any point in the intersection of two affines is that you can come up with a distinguished open of these both affines. So let P in U, which is spec AF, spec BG, U is inside of the union of the intersection, and it's a distinguished open of both spec A and spec B. Okay, so with this construction, to define this map here, we use the localization to A to the prime ideal, but we can go like factor that map through this one. Just take your element and again think A over 1 and then A over 1. And we can do that because P, I mean the prime ideal, the point coming from that prime ideal, is inside of this, for example, spec AF. So F is not an element of P, so this is totally fine. And we also can factor the same way our B to be F to BP. So when we translate that into the morphisms we get of schemes, then we have our OXP. It goes inside to U, and then we have a map to spec A, and then the inclusion to X. But then we also have this map, spec B, and include it into X. So this first map is the map we come up with first, our epsilon map. And this is our phi map, if I gave it a name. And this diagram is, again, working as inclusions into X. So that's commutative. So this tells us that it actually doesn't depend on the open you are choosing. Good. Okay. From this map, we also can construct a structure map from spec KP into X in a very similar way, looking at rings, well, fields in this case, and see the map you get there. I'm not sure, well, this is saying like you can say P as a scheme inside, as an X scheme. So I think is that the purpose of creating this map, but I'm not sure. So yeah, I think that's the goal for creating this map, like to see P, every point, because this is just one point, right? This is a field. Let me just recall that KP is OXP mod MP. So it's kind of like describing each point as a scheme itself, and that scheme is actually an X scheme, thanks to this map. So I will just tell you what that map is. Maybe you already guessed what it is. So it's take OXP and send it to the quotient, to KP. And then you get the map into spec OXP. And then you complete it with your epsilon map to X. Okay? Good. So keep in mind that way we construct this map, because we will use it just in a few minutes. Okay. I think we're done with examples. Yeah. Okay. Now the fun part. Okay. So I just show a couple of examples of morphisms. Let me just go through a new notion. Well, not new, but maybe for some of us. So let Z be a what? Good, scheme. The Z value points of a scheme X is the set, which we denoted set X, and are just morphisms, let me get this right, from set to X. Morphisms of schemes. Okay? Set of X, yeah. You mean this direction?
Yeah, no.
The notation at the front.
Oh my God. Let me just.
I think it might be X of Z.
Maybe, yeah. Yeah, X of Z. I knew it. Thanks. Okay. Yeah. So, well, so far the definition is not very clear of, okay, we just take morphisms and schemes and why we care and why we call it set value points, which are not actually points. But Nick gave me a good way to think on this. I will just tell you about this. And is what are, oh, I forgot one more thing about our notation. And if A is a ring, the A valued points of X are, we denoted XA, but we really mean X spec A. So morphisms from spec A to X. Good. Okay, so now the question. What are Q2 valued points of X equals spec Q xy mod by x squared plus y squared minus 1. Okay. So if we go to the definition, well, to answer this, we are looking for morphisms from spec Q2 into X. Okay, but these schemes have a particular structure, and is that they are also Q schemes. So, well, we will look at these maps, but let's respect the structure that both of them are Q schemes. So it means that analyze the maps from, I'll just call this R, from R to Q root 2, and we want that commutativity, meaning here that we want maps, morphisms, that fix Q. So in this case, we want to describe morphisms from this ring to Q root 2, and we want to fix all the Q points, the rational points. So it would be enough to say where to send X and where to send Y. So we send X to some value, we say Y to some value, and then to make it a morphism, we need that A squared plus B squared should be 1. So all this, what it's really saying is find points in Q root 2 that belong to the circle X squared plus Y squared equals 1. So that's a way in which we can think about like this notion. Really, in this particular case, is measuring like what can you find points on your curve that are in certain extension field of Q. So yeah, this is a good way to see like why it makes sense to think on Q value point, R value points in that case. But yeah, so in the definition, we are also very like careful on finding morphisms that keep the structure they have if they are like if they are Y schemes for certain Y, we want to respect that structure as well. Okay. Good. So let me just say one lemma. And it's if we have a morphism from X to Y, morphism of schemes. The first thing is that pi induces a map of sets from which I'll call pi set from X set to Y set. For all schemes. And the second thing is that pi is determined by all these maps. These maps of set value points, where set varies over all schemes. So this is like a good way. This is actually not a dilemma. This is a proposition. A good way to see, to describe now morphisms. So I think Nick did last time one example in which it's not enough to define the map at points because the schemes, the shift morphisms could be different. So even that they look exactly the same. But now with set value points, we are actually really determining a morphism. Okay, the first part probably you see it. Okay, so yeah, the first part is just the composition. So define pi set. So if we have a morphism here, I always confuse from set to X. So phi from set to X. Then we can map this morphism into the composition with pi. So pi. Is that the correct order? Or I think it's the other way. Pi phi. So yeah, this is just a way to come up with a map from set valued points in each case. And well, it is useful for the second part, which I still find it weird because it tells like it has to be, right? So, and it's very, I don't know. I don't like this proof. Maybe it's something wrong, so let me know. Okay, so let's say that we have another map, another morphism. I call a lot of things phi. Just use beta. From x to y, and say that the morphisms they define, the maps they define, are equal for all set. Then, in particular, when set is x, these two maps are equal. So, moreover, more particularly, if we evaluate that map in the usual identity morphism from x to x, it just worked. Then the map pi x of the identity would be the same as this. This is beta x on I. But this is pi composed with I, and this is beta composed with the identity. So actually, pi equals beta. There's a word of Yoneda somewhere in the notes. So if you know what that means, that's good. Okay. Good. Right. Okay, I will finish with this. For me, it's a theorem. It's very nice relation, but let's just call it proposition. So if we have a scheme, and let AM be a local ring. So A ring and M it's unique maximal ideal. Then two things. And we also have this map. Find a map pi from spec A to X that takes the point M to certain point P in X. Then two things happen. The first one is that for all U and X open, such that P is in U, what do you think is going to happen? So you send the maximal ideal, or the point representing the maximal ideal here, and you send it to a point, and you take a neighborhood of that point. What is going to be very useful, you will see why, is that actually U contains all the image of pi. So it would be awesome, because if you have a morphism from spec A to X, and you say that U is affine open, then actually your morphism is a morphism of affine schemes, then you just go to the rings and work in rings and then go back. That's what we will do. And the second thing, which I don't have space here, is that there is a bijection between morphisms of spec A and X and points in X such that OXP to A is a local morphism. Okay, good. I will just, I will do part A. Which it is just like topology, I think. So you pick an open that contains the point, and then we think on the preimage of the point inside of spec A, right? So if it's not equal, if the preimage of U is not spec A, then we can look at its complement, which is not empty and is closed because pi is continuous. Then this would look like as the closed set of some prime ideal. But if it's a prime ideal in A, it is inside of M. So Q is contained in M. And it means that M belongs, the point M belongs to VQ, but can be, because this is the complement of the inverse of U, but M actually is in the preimage of U. So this cannot happen. So actually the preimage is the whole space, spec A. The second part is more complicated. We'll take let me just tell you how to build the bijection. Okay, so I will call this way alpha and then beta. Okay, so to construct alpha, we have our map spec A to X, but that map sends M to some point P, and then by the previous statement, we know that this actually has a good target, which is spec A, and I'll say some spec B. And this is good because then we just think on rings. So we have from B to A this map. So define the map alpha of this from OXP, which in this case is just B localized at P, to A, the map that takes a fraction and send it to phi A, phi B inverse. There's another way to define, I think faster, to define the level of stocks. But this is like good in the sense that you can verify that this is well defined and actually it's a local morphism. Good. And in the other direction, I think that's not that bad. So if we have our map from OXP to A, then we have in the other direction, I think. Yeah. So we have the map spec A to O, spec OXP, and then what? Then we need to complete it to a morphism to X, so we can use our epsilon map that we described before. So the idea is, look that one is the inverse of the other. They look pretty different for me. But it's very interesting, the proof. It has a lot of details on how you move from schemes to rings, and also to have track of this map, what it's doing, which at the end is the map of localization. So I think I will stop here. Thanks.